go. Start recording. There we go. All right, good. I think it starts right away, but then doesn't register on there right away sometimes. But yeah. Okay, so lesson 35 will start on this slide here. But questions before we get going? What do you at? What do you got? What do you need?
Can we do 5C and 7 on 101?
101, 5C and 7. Now these, there wasn't anything posted for these. I forget now. I haven't posted some of them lately. And is that correct? Or should I just load up something and show it, talk about it?
No, there weren't any solutions uploaded.
5C and 7. Oh, the larger box thing, eh? Okay, so small box resting on a larger box when horizontal force is applied, both boxes accelerate together, the small box doesn't slip on the larger box, draw a free body diagram of the small box, and so you've done that already. Obviously, what force causes the small box to accelerate horizontally, so you get the idea that the friction force is causing it. If the acceleration of the pair of boxes has a magnitude of 2.5 meters per second squared, determine the smallest coefficient of friction that prevents slippage. So let's do this. So this is 101 5C. All right, bearings on here. All right, so page 101 5C. All right, so we're looking at a box on a box situation, and they are giving us, what do they give us here? Small box, there's not a large box. Coefficient. Not giving any mass. So I'm guessing.
Yeah, that's what I was confused about, because you only have the acceleration.
Okay, well, let's see what happens. So the acceleration of the system is 2.5. So overall, let's go like this. Overall, the system has 2.5. So let's go through it. So we're going to say, okay, so M1 has, this is the system, what they told us here, right? So basically M1 has acceleration equal to 2.5 meters per second squared also. And this is provided by, as in, already covered in A and B and so on, but it's provided by FF. We don't have, right? So let's start there for now and say, okay, FF, we know, equals mu Fn, right? If I'm analyzing everything in full, I would point out that the Fn, I want to maybe rethink my organization here. So I'm going to say provided by FF, it's mu Fn, just because I want to talk about the normal force stuff. So the normal force stuff sort of as a separate thought, you're saying that that's equal to the gravity force, but it comes from acceleration in the y direction 0. Therefore, F net in the y direction has like a normal force and a gravity force on M1, right? So that's equal to 0. And so basically we end up with pretty quick here, the normal force equals the opposite of the gravity force. So we can put that in. So we can say, basically in here, this is where we usually have like this kind of thing, right? So basically we end up writing the coefficient we're looking for times Fg, which means we can put in a mu mg, right? So m1 times 9.8. And so that's our friction force. And what else now? So that's our friction force, FF. And so then let's look at, it has acceleration, right? Acceleration equals 2.5 meters per second squared, as we've said. And we know that F net equals MA, right? So notice here right away, like you're going to have an M1. Oops, I wanted to go purple here. You're going to have an M1 in the FF, and you're going to have an M1 This is M1 also, of course. We're talking about mass 1 there, so you're going to have that as well, right? So it looks like we are canceling that out because, yeah, Fnet is, again, provided by, let's do a red star here. Red star here, this is equal to FF, right? So that is becoming, FF is mu M1 9.8. Some brackets feel good there. Equals M1 and the 2.5. Trying to draw, but it's forcing me to. This thing likes to do things that has a mind of its own sometimes. I'm gonna bring a smartboard home from the school. I think it'd be so much easier. So if we have another year of this, I'm bringing a smartboard home. I'm telling you. I don't even ask, just do it. So yeah, looks like we can solve for mu, right? So mu ends up being the 2.5 divided by the 9.8. So 2.5 divided by 9.8 gives us 0.255. I'm getting 0.25510 blah 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 blah, right? If you look back in the question, they feel they're saying they've only given us 2 significant digits. And so I guess they're rounding that up. I think get back the side of the book there says mu equals 0.3, which I kind of disagree with that rounding, actually, to be honest. If you remember the rounding rules that we've said, but they're rounding even 2 significant digits should be 2.6 anyways. I don't know why they have rounded to 0.3. Or is that not the right one? Oh no, 0.26. I'm looking at the wrong one. Okay, good. So equals 0.26 as your coefficient. Make sense?
Yep.
So I get that it seems intimidating at first when you're like, but there's no mass, like it's a panic situation because you can't calculate actual values and you can't calculate this actual number here is not known, but it's also not needed, right? So let's maybe say here this is not known but not needed. Right, it's not known, but that's okay because you can set it equal to Fnet and eventually get your masses canceling out. So no mass, no problem. Cool. So 5C done, and number 7. Number 7. 7 says an adult pulling 2 small children in a sleigh over level snow. The sleigh and the children have a total mass of 47. I meant to do these and post them, but I forgot. So I'll just show them to you. Go through them. So the sleigh and the children have a mass of 47 combined. Sleigh rope makes an angle of 23 degrees with the horizontal. So I'm just going to draw for now a block that is the sleigh and the children, and that is 47 kilograms. And we are pulling on that the rope, and that rope is making an angle of 23 degrees. And horizontal coefficient of friction between the sleigh and the snow is 0.11. So let's sort of show that we have a surface here, and we've got in here a coefficient of 0.11, if I recall correctly here. And calculate the magnitude of tension needed the rope to keep sleigh moving at constant velocity. So we're looking for Ft for constant velocity. And so this must be K. Did they tell us that? Kinetic? Yeah, they did say kinetic coefficient of friction. So as soon as we see that word here, I'm underlining it and putting stars beside it on purpose because you got to recognize that. That means, of course, that the net force is 0, right? So if we're looking for a net force of 0, then we want to have, if we're looking at the x direction stuff here, we're not lifting this thing. Does it say anything about that at all? Yeah, friction force, blah, blah, blah. No, but they're saying constant velocity, so it implies that we're not lifting anyways, right? So F net, the x direction, let's pick on that one, right? But it's in all directions, it's 0, but we've got what in the x direction? We've got an applied force, so Ft x component, and we've got a friction force, right? So in order to get this friction force, we need to recognize that we have to analyze the vertical stuff. We know Ff equals mu Fn, right? Fn in this scenario, you can't just say is equal to Fg like normal. We have to analyze it thoroughly. So for this part, we need to look at acceleration in the y direction is 0. And so we know F net in the y direction equals the gravity force plus the tension force in the y direction, right? So picture up here, we've got a tension force y component. And of course, we've got a Ftx component as well that we've already mentioned in the other starting analysis there. So that's Ftx there. And so we know this is 0. So we've got 0 equals that stuff. We can do the gravity force fully this time as a number, which is nice. And we could analyze that. I think you probably do need it this time, right? You're not going to be able to cancel m's out, but it's maybe a little bit hard to see where that doesn't happen, if that makes sense. But this is acceleration in the y direction. This is a downward force, so I'm going to put it in as the mass of 487 and the minus 9.8, because that would be a down acceleration. We're just using the typical over and up being positives, right? And the tension force in the y direction we can get. Oh, one thing I forgot in this diagram. I was looking at this and be like, wait a minute, but this, so my thought process right now, I'm just going to share with you because this is something you got to start to do yourself as well, right? My issue was, I'm saying to myself, wait a minute, that's going to give us a tension force. That's going to assign a particular tension force to this. And that's not what we want. We want to solve for the tension force needed to make this stuff up here true, right? We want to make this true with the correct tension force. This tension force, as we'd be solving for it, wouldn't be that. It would just be the tension force that just balances, and just doesn't quite lift it, which might cause it to accelerate more horizontally or less, or like who knows, it might maintain constant velocity or horizontally, or it might slow down or speed up, right? So what we need to actually include in this one is what? Anybody recognize what I missed and I forgot? There's a contact force here, right? So there's a contact force here. So this is where showing a full free body diagram might help, but I don't know. It's not much different than showing this, right? But certainly on this diagram, we could show the gravity force that's acting down in this block, right? And so there it is, right? There's the gravity force in the equation that I'm looking at. But you have to maybe sort of acknowledge or recognize that there's a contact force, right? So plus there's a contact force between the blocks, obviously, right? So contact force, don't forget about it, right? That's the normal force. Like this is a sled on the ground, so it has a normal force as well. Okay. So we know that is 0. So we've got the 0, and we've got a normal force added in here. And so we can do some things here. We can say some calculations anyways. We can do the 47 times the 9.8 gives us 460.6. And I'm not worried about numbers of significant digits here. We need to keep all digits for calculations and then round in the end to show the numbers we trust. So the FTY component, I think I could either put that in as full FT, like with the sine of the angle. So I could say like FT sine, I'll move this in a second here, sine of the 23. So put it in based on the tension force itself. I feel like we're probably going to need that. I could have left it as FTY component, but I feel like we are going to need FT sine theta. There we go, sine 23. Plus also the normal force. So right now, let's say we don't know the normal force because we don't know the tension, right? So vertically, I'd say we're, at the point where it's kind of all we can do, if that makes sense. So I might move this around so I can have room for things. That was just my reminder there, but it's pretty crazy that I forgot the normal force, seeing as it was in that friction equation that we were trying to look for, right? So you can sort of see that we're probably going to end up solving for normal force and like putting it into here, right? But let's analyze this one up here a little bit further too to see what else happens. So this is going to be 0 as well, of course, because we want to get constant velocity. That's this 0 is because we're not lifting, right? But then this 0's up here is because of the constant velocity they're telling us sideways. So this equation is going to be 0 equals the FT cos of 23, and then plus that friction force that we don't know, and we know the coefficients and so on. So if you're looking at this, once we get a normal force and plug it in and then put that into here, let's see what kind of variables we end up with. Because right now it looks like we got like a tension force, it's unknown, and a friction force, it's unknown, and a normal force, it's unknown, but the normal force is going to go in here, of course, right? So, or alternatively, we could solve for friction force in both and set them equally. There's lots of ways we could go about this. So what would the easiest way be here? Let's see. I don't always necessarily do it the easiest way first, by the way. Sometimes afterwards, like, oh, I could have done something else. But looks like normal force would be a minus 460.6. From solving out here, right? And a minus FT sine 23. So that's my normal force. So then FF from above becomes mu, which is the 0.11, times that stuff. Stop it. All right. Minus 460.6 minus FT sine 23, which we could change to a number if we want, but it doesn't really change my life much. Yeah, so now we know what the friction force is. And so that can actually go in to use. So we put the normal force, solve for it. Let's change my arrow maybe to here, I guess, right? So really that's that arrow there going in. So now we're going to put the friction force in. So I'm getting, yeah, go ahead.
Mr. Horn, where's the 0.11 from?
They gave it that. That was given.
Oh, okay. Thanks.
Up here, I'll circle it for now, but yeah, makes sense. They gave us that 0.11 number, so that's this is just mu Fn, right? I'll put another star here. This is that equation just with the normal force plugged in. So it looks like we have an equation with only one variable at that point, because we've got, we put all this stuff together. I feel like maybe going to a new page, but I'll basically put, I'll just show it like this. That the FF is going to go in there, of course, right? So let's just extend the page and then decide how we organize it afterwards. But so that equation's becoming, I'm going to say like, so, the x direction stuff, right? Call this, equation, you can number it if you want, to make it, call this equation A. And so A becomes, if you're trying to organize things, 0 equals FT cos 23 plus this 0.11 stuff. I'm just going to save myself a little bit of writing with that pen. Just doing its craziness to me. Just gonna clone that thing. Take the bits of it that I want. Except for that bit, apparently. So again, it's doing whatever it wants. Buddy. It's just supposed to be a time saver, but or at least a writing saver. And it's also kind of more obvious because it's the same color and all that, right? So I don't know why I only grabbed one of those ones and why I'm not in green. All right, green. There we go. So that's just the FF plugged in. As you can see in this formula, there is only an FT that is in the equation, so you can solve for FT. Right, and that's what we were looking for, right? Was it, did it say like find the tension force? Yeah, time to find the tension. So tricky enough, yeah, but each thing we did along the way, you know, is all justified as normal. We've done in the past where it's like, oh, the acceleration is, there's no net force, right? Because we're told it's constant velocity, and yeah. The extra complication above grade 11 stuff is this green star here. We've got this like friction equation that's as part of this process. So if we get some numbers here, you know, like I feel like I can just say solve for FT, right? So then solve and see that you get 53 newtons. Is that okay?
Yep, thanks.
Good stuff. Good questions. All right, so moving on. We have been looking at non-inertial reference frames. We're going to keep going on that and get more and more comfortable with the weirdness of it. So leading towards a little, there is some redundancy in this. So I'll say when we get to it, be like, oh, you've seen this, but that's okay. So circular motion, continuing talking about it, specifically looking at uniform circular motion. So the uniform part of it is specific, right? So that we're talking about what we want to talk about here. So we have constant speed in a circular path. I've mentioned this in previous slides. I had the little GIF or whatever you call it that was the GIF, I guess it is, because it's a G, right? That we showed the helicopter was going around and around or whatever it was. I think it was an amusement park ride. I was like, anyways, so velocity is not constant. The size in the direction, the velocity is not constant because the direction is changing, right? So it's changing. In other words, it's accelerating, and it's accelerating towards the center of the circle, which is we've referred to as centripetal acceleration. Obviously, there needs to be a centripetal force to cause an acceleration by Newton's second law, F equals ma. So we know there's a centripetal force causing that centripetal acceleration. You know, this is what's really going on, right? I'm just trying to remind us of what we looked at recently. This is what's really going on, but it's hard for people to like shake their or get rid of this idea in their head that they have from life experiences already, right? So your preconceptions, your ideas that you get based on good observations in life as smart, observant people are not quite right. So don't feel bad about it. It's just the way it is, right? So in a rotating reference frame, I'm gonna leave that one for now. In a rotating reference frame, you definitely feel like there's a force outwards, and you have to hold on for dear life and so on. Basically, your observations in life are kind of always what your brain pays attention to, and in the context of a rotating reference frame, your brain pays attention to the fact that it has to hold on for dear life, or else it gets thrown out sideways and you get hurt, right? Like you get thrown off the ride and you get hurt if you don't hang on tight enough. If you've been on one of these like merry-go-round, the circles of death or whatever you want to call them, right? They don't have these things in many playgrounds anymore because they're like a recipe for an injury, right? Like you just get going too much, and they're fun. And I think the church in Elgin actually still has one in the parking lot, and that was, you know, it'd be cool to like go there. And I don't know if that's allowed or possible right now, of course, with this ridiculous world we live in. But you know, like these things are in this rotating reference frame. If she doesn't hold on, she gets thrown off the ride, right? But the details about the throw off the ride are what we're going to try and get a hold of. Okay, so like I said, your brain tricks you into paying attention to this centrifugal force outwards that's actually truly a fictitious force, right? But I'm going to remind you, though, that in a non-inertial reference frame, that fictitious force has real effects. Okay, so even though it's an imaginary force, literally it's not an existent force, in a non-inertial rotating reference frame, it has real effects. So what did 10 say here? It was lots of words. Preconception is logical, but unfortunately wrong. It's, you know, it's your logical conclusions that you've come up with in observing things whenever you've been in something that's a rotating reference frame. Okay, so just framing, bringing us back to what we were talking about here. So let's go full screen and make it a little bigger, tackle it bit by bit. So the previous page was the inertial reference frame analysis, where we're saying like, oh, there isn't actually a centrifugal force, it's really a centripetal force, right? But so that's this analysis here, where we've got an applied force towards the center, right? That applied force towards the center has to be there to make something go in a circle, right? It's that inward force of the outer edge of the device you're inside of. If you're in a like a amusement park ride, or it's the string holding on to the stopwatch that I always spin, twirl around in room 124. So there's an applied force towards the center always, right? To be applied force, towards the center like that, applied force towards the center like that. Now these are actually listed all the same size because I'm not talking about the applied force, I'm talking about the net force. I'm talking about the centripetal force. And it's always towards the center of that circle, right? So, if there's uniform motion relative to Earth, this is what we're saying, that really there's a centripetal force towards the center all the time. My velocity is always on a tangent to the circle. So I could, go and put this velocity vector there as well. I'm not going to bother for the other one, but there's going to be a velocity on a tangent to the circle at each spot. That's what's really going on, right? Relative to Earth. So there's really a centripetal force towards the center. If we're analyzing this, we know there's acceleration towards the center. We know that the velocity is tangent to the circle, as I've said. And we know that without that applied force, right? If this wasn't available, if you cut the string of the stopwatch, twirling around, if you cut the string, then it's going to go off in a tangent to the circle. So if you cut the string at this point, or the amusement ride that you're in at an amusement park, the outer wall just broke and gave free, you would actually fly off in a straight line, like those straight lines, for example, and there'd be one at all of the 360 arbitrarily chosen degrees. So far, so good. Any questions? All right, so I just want to remind you that you can definitely look at the non-inertial reference frame, right? So if you look at the device that you're inside of and rotating, like in an amusement park ride or in a centrifuge, they call it, in a laboratory where you're like spinning things around. It's how they separate platelets from red blood cells. It's, if someone donates blood, they put it in a centrifuge, and the heavy stuff goes to the outer edge and the lighter stuff goes to the middle. And because in that rotating reference frame, there is a centrifugal force. And so the heavy stuff goes to the outer edge and the lighter stuff floats to the middle. The applied force in that centrifuge, of course, is the wall providing the center. So that's like the same analysis. We have an applied force towards the center. The difference is, let me show that, right? The applied force towards the center, of course, is needed. Now, the difference is we're saying in this non-inertial reference frame, we're saying it's needed to balance the centrifugal force to provide that zero acceleration that you have relative to that non-inertial reference frame, relative to the actual circular motion, right? Relative to the amusement park ride you're in, or relative to the centrifuge. Okay. So we're saying we have this force outward that we're feeling in that non-inertial reference frame. You do feel it, right? And it's needed to explain the motion within that, or in other words, relative to that non-inertial reference frame, or NIRF. Okay, so in this non-inertial reference frame, there is what? There's zero acceleration relative to the ride, right? You're buckled into a seat in this ride, or you're a test tube of blood inside of a centrifuge put in a little hole, and you're not moving, you're not accelerating relative to the thing that's rotating, right? You've got zero velocity relative to the ride as well, right? So I don't have a velocity vector on here because we're actually looking at this whole thing as a, you're inside of it, so you're not moving relative to it. What happens if the applied force is no longer there in this rotating non-inertial reference frame? In this one, we acknowledge that what's really going on is a circle relative to Earth, and so you would keep going with a straight line. Your inertia would take over there, right? So right now you're working against inertia, against the ability of the object to not change its motion. That's what inertia is, right? Its mass causes it to not change its motion, but we are putting a force towards the center all the time, making it travel in a circle, even though it wants to just go in a straight line. In this one, if I cut the string, I don't have the force towards the center anymore, then what would happen? We wouldn't have this applied force anymore. So what's going to happen? There's a centrifugal force out from the center of the circle. And so from the viewpoint of within the circle itself, from the non-inertial reference frame viewpoint, you absolutely would see something go straight out. Okay? Without the applied force, you're visualizing it there now in the circle, right? The object would go in a straight line out from the circle. So it would actually go this way. Okay, but keep in mind that what is possibly in air quotes, if you want, really going on is that even though it looks like it's going straight out relative to the circle, this rotation, right, that's really going on when we snap back into the real world of the relative to the Earth reference frame, right? So we know really we have, there's a slide that later on in a lesson that sort of shows this, but what's really going on, of course, is that outward distance. It goes, let's say it goes out to here, but in that time it rotated to here, right? And then in the time it goes out to here, it's rotated over to here. In the time it goes out to here, it's rotated over to, get my drift here? So it would rotate it over to here. And so really what's going on is it's going this way. But it absolutely, from this point of view, when you look at it from this angle, and then from this angle, and then from this angle, and then from this angle, it looks like it went out. It looks like it went out to here, and then out to here, and then out to here, from this rotating reference frame point of view. So I'm trying really hard to help you understand in your gut, maybe your brain too, rotational reference frames. Okay, if you get to the point where you understand this and you talk to someone who hasn't taken a grade 12 physics class, they're going to think that on a merry-go-round there's a force out, and you're going to have to try to convince them, teach them really the reality of the situation, and this is all part of it. Okay, so things really do go out, absolutely, right? You'll see videos of it later, but it's from this reference frame they go out. In the real reference frame, what's going on relative to the Earth, it would just be going straight. So I feel like I have explained that well. I hope you agree. So the issue is, of course, hopefully you see this, is that these descriptions are both true. Right? It just depends on what you're viewing relative to. It depends what your reference frame observations are relative, our descriptions and so on are relative to. Any questions? Is it making sense?
Mostly.
Yeah, crickets. Yeah, it is weird, so it's going to take a little bit for you to feel confident with it, maybe, or maybe it's like, you know what, this makes perfect sense. I'm I'm hoping, of course, in my optimistic world of view, you're someone to say, yeah, I get this now. This it seemed weird before, but I'm getting it more and more. So picturing this girl here, you know, she's feeling this centrifugal force, that fictitious force in her rotational non-inertial reference frame. So she's holding on for dear life to balance that so she can stay in zero velocity, zero acceleration relative to this bar that she's holding on to as she spins around, right? If she lets go, obviously then this force that she's feeling is going to send her out. But in reality, it would actually send her out on a tangent line, like this page is going to be dedicated to this redundant page is going to show. Okay, so you know these people have these chairs mounted on this one. These chairs, the back of the chairs, clearly providing a force towards the center to allow them to go around and around in a circle instead of just flying off on a tangent velocity. Right? So this girl would likely describe the experience as holding on against the force she's feeling outwards due to the circular motion. What's really going on, really in air quotes there, a little bit, she's holding on and applying a force towards the center of the circle, which causes an acceleration towards the center, which keeps her traveling in a circular path. Okay? So the free body diagram for her, this is the inertial reference frame. Free body diagram is just a force towards the center. Okay, but obviously that doesn't describe her motion relative to the bar she's holding on to. You can't just have a force towards the center. You have to have, you know, to be zero velocity, zero acceleration relative to the bar, you have to have a balanced force situation. So the outwards force she thinks she feels really doesn't exist, right? It's referred to as a fictitious force. It's often called a centrifugal force, meaning center fleeing. So it really doesn't exist, but we should say like really doesn't exist like in the inertial reference frame, right? So it really doesn't exist relative to Earth. Or whatever your inertial reference frame is, right? You know, I just add just to have complete information on each page, but it does exist in the, am I okay to say NIRF, non-inertial reference frame, i.e. viewing from the rotating reference frame. Rotating reference frame. So in that rotating reference frame, you'd say, oh, well, you know what? I've got an applied force, but that's really balancing this centrifugal force that I'm feeling. And of course, in this reference frame here, in that rotating reference frame, we've got a net force of 0, which explains why there's acceleration relative to the acceleration equals 0. Let's just say acceleration equals 0 relative to the bar she's holding on to, you know, the bar or whatever, the bar she's holding on to. Yeah, let's do that. So, yeah, this took me a bit back in the day when I first started teaching this to really get a handle on, because my teacher didn't really talk about non-inertial reference frames at all. It was totally neglected, and so I was like had it hammered into my brain that centrifugal force is fake. It's fake news, you know, or whatever. But you really do have to include it in a non-inertial reference frame to describe things, which is different than what I was shown originally. So hard to shake that once you've seen it and had it forced on you so much. But anyways, hopefully I'm doing you a good service here. So this is the idea of that, you know, if you're going around and around, and if you all of a sudden didn't have an applied force towards the middle, you would just keep going straight, right? And so she'd think that she's going out this way, but actually she'd end up going with that straight line. And I showed on the other page there too, that in the time that you take to go here, right, as in the time you take to go there, you have also rotated out to, I guess it would be here, right? That same distance. So let's say delta t for this also gives you this, right? So delta t leads to a delta d and also a delta theta, let's call it. Good with that? So she actually would rotate to there, and then let's do one more. She'd go out to here, she would go out to here, right? So delta d for this one, right? And so on. So yeah, she would actually have rotated to there, and actually would have rotated to here. So hopefully that's helping you have the two things be okay in your mind. They can both happen. You can go straight out relative to the ride, and you can go straight out, or you can go on a tangent as well. MIT, yeah. Let's go for this one here. First, this ad from who knows what. So this little guy here, this little video, they have a rotating spinning wheel, and they have a little ball attached to it, and then it's going to be spinning, 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 and there's going to be a knife that cuts the, it's actually going to spin this way, and the knife cuts the string right there. So basically, if this ball is spinning around and around and around, and they cut the knife right there, we're saying, oh, it should have a tangential velocity, a tangent velocity straight up at that point, right? If centrifugal force was true relative to this inertial reference frame, this person standing on Earth, stationary to the physics class or whatever, right? If centrifugal force was a real thing in that reference frame, the ball would fly straight up and hit him. If our analysis of an inertial reference frame is true, then it'll go straight up. That's what's going on here. So let's get it spinning, and then they cut the string. It's a little hard to see where the ball goes in this one. Eventually cuts the string. I'm not sure why he waits so long. Here we go. So it's not super easy to see there, but you can tell he's picking the ball up off the table. The ball went up, and in the next view from the front of it, you'll be able to see it better because he catches it. So spinning, spinning, spinning. Ball's going around and around like this. It's going to be cut right there. The ball's going to go up, and he's going to catch it like a superstar. LOL. And cut, and catches it even. It does kind of, it's not cutting it quite the perfect spot, I think, because you see how he catches it kind of over here, but clearly it went up and then went like this. So it came off with a little bit of an angled velocity by the looks of it. So it went in projectile motion like this, like that. By the way, projectile motion, I've completely skipped it for this course. You might have noticed earlier in the textbook there was projectile motion questions in the units or whatever. We covered it in grade 11, so I'm not even talking about it. Anyways, so yeah, that is showing that's true. What do we have here? So this is the merry-go-round, and oh yeah, this, you know, not everything you see on the internet is true. Big shocker, right? But if you start looking up things to try and help yourself learn this, it's very possible you're going to find incorrect information. So this merry-go-round, playground spinning thing, I don't know what it's really called. So does it have a merry-go-round? You know, if so, you know that when you ride it, you have to hold on at all times or you'll get thrown off. The details of being thrown off we've talked about a lot. The force that would make you fall off or get thrown off is called the centrifugal force. And the centrifugal force pulls spinny things towards the outside of the circle, directly out away from the circle they're spinning in. Right? So if that's all you ever read on the internet, you'd be like, oh, geez. I'll come back to that one in a bit. So, you know, basically here, the thrown off idea is, I'm correcting it here and saying you're really going to keep going tangentially, not really radially outward as they're implying. So the force that would make you fall is called the centrifugal force, and the centrifugal force, blah, 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 does all this. Really, we're going to say here, you just end up keeping your velocity you had when you go? If you hold on times 6 feet through. Yeah, when you let go. I just was looking at the details of this, which is because you have inertia. So in inertial reference frame analysis, that's what we're saying, right? But again, I'm not going to write it here, but from the viewpoint of someone who's, say, in the center of the ride, spinning with, they would agree. They would see the person thrown off relative to their point of view if they're in the center of the ride, just holding on, spinning with the ride. Okay. They try to explain this further by saying more wrong stuff. So they hold a half full bucket of water beside you in your hand, and if you quickly swing the bucket around your head, overhead in a circle, if you swing it fast enough, you can swing the bucket around as many times as you want, the water won't come out. Were you surprised to not get wet? The water was held in by centrifugal force. You'd be like, ugh, the water was held in by centrifugal force. And the answer is, yes, from the, I'm going to say here, yes, from the view of the non-inertial reference frame. But we can't ignore the fact that in reality what's going on is we have a inertial reference frame of the Earth that we're standing on when we're spinning this bucket. So we want to be able to analyze it both ways, right? So right here, it's like what's held in by the centrifugal force. Be like, no, actually the water has inertia and wants to keep going straight. So instead, the water is actually being pushed by the centripetal force towards the center of the circle, right? So the bottom of the bucket is pressing on the water to make it go towards the center. Like, think about it. If the bottom of the bucket fell out, what would happen? The water would just go in a straight line, tangent to the circle, right? From the viewpoint of being in the middle of the circle, it would look like it goes out, but in reality, that rotation leads to it going on a tangent, straight out. So this was asked about earlier in the course, so I included it here in a little bit more detail. So that, and we're actually going to hit these free body diagrams and circular motion in more detail in another slide. But first kick at it here. Picture the water in the bucket, and it has a gravity force of 10 newtons on it, right? If you just held it above your head upside down, clearly the gravity is going to cause the water to fall down onto your head. It's going to accelerate towards you, right? If the net force needed for circular motion, it wasn't quite clear enough here, but if their circular motion is fast enough, that the centripetal force is greater than the gravity force. So here we go. We've got an FC and an F net needed, right? It's FC here, centripetal force. There we go. Is 30 newtons. Think about the free body diagram of this thing and think about the forces involved here, right? So we need to have a centripetal force. Now the trick is, and there's going to be lots more times that I'll say this, but you got to make sure not to put FC in this equation. Can someone key their mic, please, and tell me why FC is not listed in this equation?
Because it's not an actual force.
Yeah, well, it is the net force, right? FC is the net force. So FC is the result of all the forces that added up. So yeah, exactly. So FC is the net force, and so FC is negative 30 in this case. We're saying that we need to have a centripetal force, a net force of all of our forces added up, downward 30. So there's that minus 30. That comes, in this scenario, from a gravity force of 10 down, so there's the minus, and the normal force from the bucket, right? So if you look at the water has a free body diagram on it where it has a gravity force and it has a normal force, but it's a little hard to figure out what that normal force would be in this diagram, right? The way it is, until we do the math and we see that, oh, so the normal force in this case is minus, why did I forget the minus here, right? Clearly when I add the 10 to both sides, I'm going to get a minus 20. So add 10 to both sides, I'm getting a minus 20, right? So when I go and add the normal force onto this thing, then it looks like this. Twice as big. We got the minus 20 normal force, right? So what's happening is our free body diagram looks like this, right? And really that normal force, it's like right now you're sitting on something, doing this lesson, watching this stuff with me, you've got a normal force like pushing you up to hold you against gravity. This would be similar to that. This would be, you have a normal force down holding you steady in the bucket, traveling in this circular motion. So the water would be held in by the 20 newtons of normal force, right? In that situation. Let's say here, I guess it would be an inertial reference frame, eh? That one, because we're analyzing actual centripetal forces and so on. So that's wrong when I was typing this out. I should get rid of that. Anyways, yeah. So basically, the water, as the water falls, say to this height over here, right? As the water falls to that height over there, like it actually moves sideways with velocity and ends up over here, and the bucket stays with it. You know, like it's actually staying with the bucket as the bucket rotates. Actually, the bucket would have, of course, turned this way, but you get it. Hopefully, all of this stuff would have turned. So that's the true analysis. And then at the bottom, what's the difference with the bottom situation? Now the centripetal force, the net force in the centripetal force is now up, right? So this is our centripetal force still. Notice that it's up now, right? So that means we got a positive value for the net force, right? So now it actually gives us a normal force of 40, right? So the free body diagram is going to look like this. We're going to have a 40 up and a 10 down, combining to give us that 30 that we need for the centripetal force, for the, just that constant 30 towards the center that we need. And that's, yeah. So basically, if you were inside of a bucket and they were spinning it, say it's some amusement park ride somewhere where you just like swim in a bucket of water and it spins you around vertically, like you would feel much more force on you at the bottom than at the top, right? Because the force you'd be feeling on you would be that normal force acting to keep you going in a circle. In the bottom, you'd have 40 newtons of normal force. In the top, you'd only have 20 newtons of normal force, but there's enough force on you to make you go in a circle that you don't actually fall down when you're up here. But it definitely would feel like you'd feel lighter here, and then in the bottom here, you'd like feel like you're getting crushed into the water. Like, I don't know if this is, you probably die, to be honest, if this is like you're swimming in here and so on. I'm guessing that would probably not work out so well. Probably won't build that ride in my physics amusement park if I win $1 bazillion. Anyways.
I have a question. I'm not sure I understand why the normal force is negative in the first example.
So the normal force is negative in this context here, the way we're solving it out, simply because it's down, right? The math shows us that it's down. So it came from, Sarah, the fact that our centripetal force is down, because in this situation, at the top, we have to have a downward force, right? It's the net force is down to make it go in a circle arcing down. So that forced this minus 30. And then the math just led to the conclusion here that, so we'd have a minus 20, right? So that led mathematically to the normal force being down.
So like the force down so that it would stay in the bucket.
Yeah.
Okay.
Because there's a force needed down to keep the water in the bucket. That's what's in flipping the viewpoint. That's what's keeping the water stuck in the bucket. Does that help?
Makes sense.
So picture if you had this thing rotating around and we had, if it was going slower, so let's picture a slower version of this where FC needs to be 10. Okay, so if FC in this case is minus 10 because it's down, right? So we've got this net force of down. I should put a minus on there, I suppose, but it's in the direction system there with the arrow. I didn't feel was necessary. But if we had a slower rotating bucket and we had a net force of 10, then we'd end up with the minus 10 equals the 10 of gravity down plus the normal force, right? That would lead to a normal force here of 0. So this is you're swinging the bucket so slow that the water has no normal force on it at all, it just follows with the bucket. Like if you were in that ride in an amusement park, you would feel weightless, right? You would be experiencing what I think is a way better name, normal forcelessness. At the top of that rotation, the gravity would provide the force at that instant needed for you to stay in circular motion. You don't need an extra normal force to make you do it. Okay, so we can even actually talk about weightlessness as part of this analysis, and that as a separate slide next time around. But if you go slower, right, you'd be experiencing normal forcelessness. Questions? So this would be weightlessness, or in other words, or normal forcelessness, right? Not sure if that's spelled right, but it's not even actually a word, so I guess I can spell it however I want. Centrifugal force, we're thinking is that perceived outward force. Centrifugal force is a fictitious force. Doesn't actually exist, right? But you know, this is harsh wording here actually. It doesn't exist, but it seems to in a non-inertial reference frame. So I don't like that wording. You know, in a non-inertial reference frame, it's needed. So I'm gonna say it's needed in the non-inertial reference frame. Okay, I'm trying to shake my harsh wording from my original training, original schooling. That's right, and I guess I never noticed in university. We never talked about it. I don't know, I'm not sure. I think the best explanation for this is you never really understand something quite as well as until after you've taught it, because it forces you to just really start to understand it. Otherwise, you have trouble basically trying to explain things, of course. So I've ended up understanding this better, of course, as I've taught it many times. So what's really going on, of course, is inertia. It's due to inertia in this inertial reference frame idea, right? And then basically you're observing with respect to a non-inertial reference frame, and so it seems like, or there are other forces needed to explain the motion. So this is you know, this is on this version of this page from further ago in my thought process is, you know, we're saying like, however, there's a real effect, of course, in a non-inertial reference frame. That's why I'm saying it's needed, right? So it's a needed force because it's a real effect. And so in a centrifuge, for example, you know, you really do have this outwards force. And so this is something I could do in 124 as well, but seeing a video is very similar. So I have an aquarium and I've got a little spin table and I can, you know, strap it to it to keep it from falling off. But you spin this aquarium around and the water gets thrown outwards, right? Why is the water getting thrown outwards, sloshing to the edges? Well, there must be a force pushing it out to the edge, right? If this aquarium was just sitting in the middle of a room in some science fiction reality, you'd say, oh, geez, there must be a force pushing outwards all the time. And notice that it's out to the corners as well because of the way it's, you know, shaped. And then a mathematician comes along and says, ooh, I'm going to figure out an equation for that. And then a physicist says, ooh, I'm going to use that equation to describe something in real life. That's how it works. And it's funny because the physicists would say, why are you bothering to make that equation? Until later on when they're like, ooh, I'm going to use it to describe gravity. You know, like it's, anyways. Yeah. So centrifugal force, we're saying it doesn't really exist. You know, like remember we talked about the car stopping and the apple fell off onto the floor, accelerated onto the floor. There wasn't really a force causing an acceleration on the apple. So this the exact same as that force causing the apple to accelerate forward being non-existent in a stopping car. This one's just as non-existent, right? But in that non-inertial reference frame, it is needed and it makes sense. So I'm just trying to tie those two situations together because I think the car stopping one's easy, right? To picture. Circular motion, we get all messed up. We get all dizzy basically trying to talk about circular motion. As humans, we tend to. So circular motion videos. What do I say there? There still isn't any force outward in reality, even though it looks like this. Oh, the Russians. I love them. So they are spinning this merry-go-round thing by wrapping a rope around it and pulling it with a car, thinking this will be fun. Ah. Oh my God. So that person is like hanging on for dear life, right? Because they need to in order to provide a big enough force towards the center to have that circular motion. They, of course, probably feel like, oh, he's getting thrown outwards, and then someone comes to try and help and so on. But yeah, they're like, how do I catch him without breaking his spine? Gotta be careful here. Anyways, so that is extreme merry-go-rounding. Please don't try that at home. We get confused and dizzy because of our reference frames, right? When you're looking within a non-inertial reference frame, you make sense of the world that you're experiencing. And you're experiencing a world that is very weird. And so these videos aren't really related, but basically someone puts like a GoPro on the end of a sword and does a video. And you're like, you get kind of messed up by the viewpoint from within a rotating reference frame, right? Like, what is going on? It's like weirder than you'd think from that viewpoint. So he's spinning the sword around and around there. Anyways, so yeah, it's not surprising we get confused by that. Oh, this is the sword. Well, that should be the same one, I think. Sword frame of reference. Why do I have it? Different link. Maybe it's just a different version of it. Oh, okay. This is a spinning reference frame. It's just a different video of it. Yeah. Are you dizzy yet? Yeah, I am too. So, the person's going to show it going around in a circle. Maybe. Sometimes they don't do quite what I want. I want to just spin it around in nice uniform circular motion and show the viewpoint from both. But, oh well. So the direction of it, let's just peek at the direction of it briefly, and we'll see this again in when we do the equation. But work with me here. Picture right here, that velocity is the initial velocity, and then this velocity is the final velocity. Just picking two velocities, v1 and v2. Okay. What direction is the acceleration if you have a v1 and a v2? You know, split down the middle basically. Picture where you'd have this, where you'd have v1. We want v2 minus v1, right? Like normal. That's a delta v. And so I want v2 plus negative v1 if we're doing that version of doing subtraction. You can see you end up with an acceleration vector that's towards the center, like that, between those two, right? Between v1 and v2, you got this acceleration towards the center. So our analysis in this little diagram here actually shows the circle. So this is v1 right there, and then v2, and then in the middle, though, it's kind of nice to be able to show like in the middle, it was towards the center. So that's why I've shown it to you the way I have, right? So which way is the net force? Well, the net force is towards the center. It's the centripetal force. Net force is the centripetal force towards the center. So this page, just quickly and easily, loosely here, kind of shows that the acceleration really is towards the center. If you picked any two initial velocities and final velocities. So if this is v1, and then this is v2. If I try to do this on the fly here, right? If I even put them tail to tail. So let's actually clone that so I can keep a record of where they were. If I put them tail to tail, we know that v2 minus v1, so we're looking at final minus initial. So this is the final, and this was the initial. And so my acceleration must be like that. I'll check it out. If I go in the middle of all of that stuff, where am I pointing? I'm pointing towards the center of the circle, right? You're sort of, I'm roughly speaking there, but yeah, acceleration is towards the center based on the changes in velocities and everything. Okay, so I've said this enough times. I know you're probably already good with this, but we're not putting the centripetal force on a free body diagram because it's, of course, the net force, right? So it's just a page dedicated to that. So we don't list FC in here as a force. We list it as the result of all the forces added up. Okay? So net force in circular motion is FC. So just make a note of that if you haven't already multiple times. And I just need to remind you that so that when we analyze these free body diagrams, we're not making that classic mistake of listing FC on the free body diagram as a force. So we've already done this with the bucket of water, but basically picture position 1, position 2, position 3, position 4, and position 5. Okay, just going top, bottom as the key ones to analyze. 3 and 4 are very similar, they're going to be easy. And then 5 is weirder when you're on an angle. But in position 1, we know we have a tension force down. If we have uniform circular motion, right? This is horizontal to keep it easy. Okay, it's horizontal circular motion viewed from above. And so we know there's a tension force towards the bottom. In position 2, or towards in the picture, but yeah, tension force towards the center, down from this point of view. In position 2, of course, you'd have a tension force up from this point of view. Position 3, position force towards the center, so that'd be to the right. 4 towards the left, of course, and then on a diagonal at position 5. So this shouldn't be a hard page at all. You zoom entire page, get the ideas of that. And so then, just like we did previously with the free body diagram for the water, which was in here, you just have to be careful about like what direction things are in, whether you're putting it as minuses or pluses, ups or downs, right? So from this point of view, it is actually seeing as an up or down. So position 1, let's go view full screen again, or page width, I should say. We're putting in, we have at the position 1, the centripetal force must be down. So it's going in as a minus value, right? And so that's where we'd say, okay, well, we've got this minus 10, right? This minus 10 must equal a gravity and a tension force and so on. So these are just numbers. Like if gravity was only minus 7, then there'd be this additional force of 3 needed, right? I can't say here if gravity was, I can't say if gravity was minus 100, because then it wouldn't be in uniform circular motion. Well, actually, it could be. What would the tension force have to be if the gravity force was, I'll just do this. So if Fg equals minus 100, and we still need this, Fc is minus 10, right? We'd have Fc equals Fg plus Fn. We'd have minus 100 would equal minus 10 plus the normal force. And so you'd say, oh, okay, so we need a normal force of, yeah, is that right? Yeah, so normal force, we'd add it and we get minus 90. What am I doing wrong there, though? I need to, the way I'm thinking of this, if gravity force is too strong for we're going to end up with a normal force that would be up. Why am I not getting a normal force up? This is the danger of thinking on the fly sometimes. It's messed up. Because I'm showing here that if we need if gravity's too strong, it would pull down and we'd have to hold it up. Where am I? Oh, I put it in. I'm surprised no one's keyed their mic include me in yet. I put the 100 in for FC. I'm saying if the gravity force is 100. I can change my, all right. Knew what I was supposed to get, but I just put it in the wrong spot. So if the gravity force is minus 100, and the FC is still that minus 10 for the circular motion we're doing, what would the normal force have to be? Add 100 to both sides, we get a plus 90, right? We got plus 90. So can this thing be, if it's actually vertical circular motion, right? But with gravity involved, could this be a string that's whirling the bucket around? Can a string push up? No. So it would have to be like a rod making this go, right? In which case, then the water certainly would fall out because you'd have a rod pushing up on the bucket to stop it from falling. If the water's free to fall, it certainly would. Okay. So this one, I just noticing here, we started out talking about horizontal circular motion, and then of course we've analyzed, that's too easy, right? Like horizontal is just, oh, the force is always towards the center. So I didn't emphasize when I first came to this page, we're talking about vertical now. Okay, so at each spot, again, we're going to analyze out, and of course we still have the centripetal force towards the center, like we analyzed, and we can talk about the forces involved with the normal force, right? But the key was to notice that the centripetal force was minus 10. It's down in this position, right? So right here, acceleration direction, let's add that it's down at 1, right? At this position, the centripetal force would be down. What about position 2? Centripetal force would have to obviously be up, right? And so in our math, we're going to have a positive 10 put in. So there's the positive 10. So again, I'm just going to show, it's a little easier to show positive 10. So positive 10. And what would that lead to? Well, if we want a positive 10 result, this would have to be positive 17, you can tell, right? If you solve this out, add 7 to both sides, but that would have to be positive 17. So in other words, you got lots of lift force needed to make this thing go in vertical circular motion, as we talked about with the bucket. Position 3 obviously has to have a centripetal force towards the center of the circle. So basically here, if we're talking about x direction forces, if we're talking about F net in the x direction, centripetal force, then the only force, right? The only force is the tension force. Right? The only force that's affecting circular motion is the tension force sideways. Right? So basically the tension force would have to be 10. And repeat that analysis for position 3, but it'd be to the left. So this was 4 and 3, whatever. Right? So tension force would be to the right. It looks like I labeled it backwards, but anyways. And then what about the angle one? So picture the angle one. Obviously, we have to have a centripetal force here causing this centripetal acceleration. So a centripetal force on a diagonal, that is going to be made up of partially tension force and partially gravity. So picture gravity is down. There's going to be a component of gravity that way, and there's going to be a force, a tension force in towards the center. So there's going to be a component of the gravity away from the center and a tension force towards the center. That's that diagram. So if gravity was, again, still -7, and say maybe the component based on the angle rad is -4, then you could solve this out. You'd say, oh, well, if this has to be +10 because we've analyzed, our direction system is this, right, towards the center. So I'm going to say +10. I've got a -4. The force would have to be 14. So that should be doable for you just based on previous knowledge of algebra, math, and free body diagrams. Net force equals all of them added up. So that's our 10, our net force is centripetal, and so on. All right, any questions? So whatever spot you pick in a circle, you have to be able to analyze the free body diagram. It starts with picking the direction of the centripetal force. My lesson is slow to respond. Give me a moment. Maybe it's my screen doing its weird thing. There we go. So this is the old video. The rest of it. So again, it's so old but so good. So let's watch that. Let me go from there as well. I don't think it has ads. They weren't. This could be why things are slow. Let me free up my computer a little bit here. So this is part 2. Looks like it's ready to go.
So far, we've been talking about frames of reference moving at a constant velocity relative to one another. Now I'm going to do the experiment with the dropping ball again, only this time the cart will be accelerated relative to the Earth frame. These weights will fall and give the cart a constant acceleration. Put the ball up, and then I will release it. The motion is very fast, and I want you to watch at the point where the ball is released from the fixed camera. Ready? I don't know whether you saw that or not, but the path of the ball...
So just pausing quick, did you see the projectile motion it went with?
And then I will release it. The motion is very fast, and I want you to watch at the point where the ball is released.
You're going to see the
from
ball
the
go
fixed camera.
down like this on a curve.
Ready?
Projectile motion. So right there you saw a little blur that went like this, right? Projectile motion.
I don't know whether you saw that or not, but the path of the ball was the same as it was before. Only this time it landed in a different spot.
So he's saying the path is the same as it was before, but I'm not sure which before he's referring to, but he explains it coming up here anyways.
This is because the car kept on accelerating in this direction as the ball was falling. Now I'm going to let you see it again with the slow motion camera fixed onto the car.
So with the camera fixed onto the car, we're talking about a non-inertial reference frame. So it's going to look a little weird. So the ball magically falls diagonally backwards, right? So in that non-inertial reference frame, he's going to talk about how you'd have to imagine there being a force, I guess, pushing backwards on it to make it go on an angle as it falls. It's got gravity plus also some other fictitious force backwards, right?
Moving off to one side and not following down the vertical reference line as it were in the constant velocity.
If they didn't have the tech to be able to do this, but if they had a camera here pointing straight down, then you would have seen the ball go straight down. That's what he's saying. Like it fell the same as before. He's glossing over the fact that really it actually went with projectile motion down. But from this point of view, you'd see the ball fall this far as it goes sideways, and then you'd see the ball fall this way as it goes sideways, and this way, but all the while the camera would be going sideways too. So from this point of view, you would see the ball fall straight down just like before, is what he meant from the previous time. Anyways.
You were in this accelerated frame of reference. How could you explain this motion? Gravity is the only force acting on this ball, so it should fall straight down. But if the law of inertia is to hold, there must be a force pushing sideways on the ball in this direction to cause it to deviate from the vertical path. What kind of a force is it? It isn't a gravitational, or an electric, or a nuclear force. In fact, it isn't a force at all, as we know one. So we're left to conclude that since there is no force, could be pushing in this direction on the ball, but the law of inertia just does not hold. This is a strange frame of reference. We call a frame of reference in which the law of inertia holds an inertial frame. The law of inertia holds in the Earth frame of reference, so it is an inertial frame. The cart moving at constant velocity relative to the Earth is an inertial frame, but the cart which is accelerated is not an inertial frame.
So he's saying here we got strange behavior. This is a non-inertial reference frame.
Because the frame of reference that we're used to living in is one in which the law of inertia holds. When we go into a non-inertial frame, like the frame of the accelerated cart, our belief in the law of inertia is so strong that when we see an acceleration of the ball sideways, we think there is a force causing it.
So that's exactly the issue for their brains, right? We're so used to inertial reference frames, so when we see the ball going sideways like that, we think, oh, there must be a force causing that.
So we make up a fiction that there is a force. And sometimes we call this a fictitious force. Fictitious forces arise in accelerated frames of reference. The frame is accelerated in this direction, so you in the
So we're switching to something else now. And he's going to say, okay, so what's going on now? Like we're analyzing that stuff and we're getting the idea of non-inertial reference frames, the behavior looking weird. Now he's going to show you another weird behavior. Okay, so watch this. So he gives it a little push, kind of like diagonally there.
Why doesn't the puck move straight across the table as it did before?
So he tries to push it towards his partner there. And the puck does that. That's kind of weird. If the table was just on a slant, it would just go forwards and backwards. I suppose you could probably make it do that by like grabbing the table and tilting it left, right, up, down, you know, like to make it happen, but that's not what's going on. So
as you can see, it doesn't. So if we believe in the law of inertia, then we must believe that there is an unbalanced force to change the velocity of the puck. But this puck is nearly frictionless. So what can be exerting this unbalanced force on it?
So
suppose that you watch the motion.
I'm going to stop before he shows from the other point of view, but they're not telling us, but basically this viewpoint is from a non-inertial reference frame. It's not from an Earth reference frame. And so when you're picturing this thing going around in a circle, we definitely are picturing that there's a force towards the center, making it do that, right? Like it's tied by a string or something, or it has a little jetpack on it, blasting towards the center. That's the centripetal force that would be needed for this motion to happen. But we're not in an inertial reference frame, we're in a non-inertial reference frame, and he's going to show that now.
Suppose that you watch the motion, this time through a camera which is fixed in the Earth's frame of reference.
So this camera from above shows the table and the platform they're sitting at is actually rotating. And try not to get motion sick watching this. And right now it's sort of hard to actually see what's going on. And eventually they show other camera views. He says, like, if you just focus on the
See that now the puck is moving.
Okay, now I might have gone too far. Better just let it play. There we go. This is the part I wanted to show. So when you're just viewing the puck itself, it's really hard to focus on what's going on. It looks like it goes up and down and all over the place.
I think if you concentrate on watching just the puck, you can see that it is moving in a straight line.
So he's saying if you concentrate, you focus on just the puck, you can see it's moving in a straight line. And at this point, I'm with you. I don't believe him. But
and
watch.
Therefore, there is no unbalanced force acting on it.
So right now, even right now, looking at this view, I still don't see it. But watch, they're going to put a line in to show you what it's really doing. It's actually just going sideways. So that was the same video clip, just with the line shown so you can see what it's really doing. So that one's moving on a bit of a diagonal. But it is just traveling with a straight line.
Now we're going to stop this rotation so that I can talk to you about what is happening here. I don't know about you, but I'm busy. In the first fixed frame of reference, there was no unbalanced force, but in the frame of reference rotating in this turntable, there was an unbalanced force.
So in the non-inertial reference frame, there's an unbalanced force. It's not traveling a straight line from his point of view, right? But from the Earth's reference frame, of course, it is just obeying laws of inertia.
Because the velocity of the puck kept changing. This was a fictitious force. The rotating frame is a non-inertial or accelerated frame, just as the accelerated frame of the cart that Dr. Hume showed you was. You know that every object which is moving in a circle has an acceleration towards the center of the circle. This is the acceleration that has a special name, the centripetal acceleration. Now you hold this puck for a while, hold it steady, while the turntable is rotating. I'll get off. Are you ready? I'm ready. Start the rotation.
I'm ready. So he's holding it with a string.
You can see that now the puck is moving in a circle. Dr. Hume is exerting a force to keep it moving in the circle, and you can see this from the fact that the rubber ring is extended. He is exerting the centrifugal
So if I remember right, they'll
force.
let go
This is the
and see
only
which way it
horizontal
goes.
force acting on the puck.
And I'm hoping they're going to make it clear that from one point of view, it looks like the puck goes straight out radially from the center. And from the other point of view, you can see that it goes tangentially in a straight line.
But now let's look at it again from his point of view in the rotating system. He is exerting a force towards the center of the table, and yet the puck is standing still, at least more or less still. There is some vibration.
So in that point of view, there must be a centrifugal force out to balance that applied force in, right?
Now, he believes in the law of inertia, so he thinks there's an equal force on the puck away from the center of the table, so that there is no unbalanced force. This outward force on the puck is a fictitious force. In this case, sometimes it's called the centrifugal force.
Centrifugal or
In
centrifugal.
the fixed reference frame, there is no outward force on the puck. Now, suppose that Dr. Hume stops exerting a force.
There we go.
Drops the puck. In the fixed frame of reference, the puck moves off in a straight line. There is now no unbalanced force acting on it. Now let's look at it again from his point of view in the rotating system. When he releases the puck, which to him was at rest, it moves. The force away from the center is now an unbalanced force on the puck to him.
I'm not sure if that was
Remember, to us,
what I was hoping for,
on the puck is fictitious.
but this
In our
one,
earth frame of reference, now he believes in the law of this outward force on the puck is the fictitious. In the fixed frame of reference,
here we
the
go.
puck.
So
Now suppose that Dr. Hume stops exerting a force.
see how, like,
The puck.
picture at that point, there was a circle like this, and he let go here, and it went off in a straight line, right? So I'll just try and show that just one more time here. Where would it be about there?
In the fixed reference frame, there is no outward force on the puck. Now suppose that Dr.
So we've got a circle going like this.
stops exerting a
Let's
force.
go right there, and the puck goes
Drops the puck.
off in a straight tangent. Okay, so I wish they would draw. They might actually yet in the video because the video's a bit slow. Get to it eventually, maybe.
In the fixed frame of reference, the
So
puck
that's the
moves off in a
inertial
straight
frame of
line.
reference where you can see there's
There's
rotation
now
going on.
no unbalanced force
And then they
acting on it.
show from the
Now
non-inertial
let's look
reference
at it
frame.
again from his point of view in the rotating system.
So
When he
he's going to
releases
see
which
the
to
puck
him
just
was at
basically
rest,
go
it
out
moves.
from
The force
the center. Kind of went a little weird there, but
away from the center is now an unbalanced force on the puck to him. Remember, to us, the outward force on the puck is fictitious because in our Earth frame of reference it doesn't exist. But to Dr. Hume, in the accelerated frame of reference, it's a perfectly real force.
that's the part that I remember missing originally. Is in his point of view, it's a perfectly real force. It's perfect. It's existing. It's has an effect. So of course it's there.
I hope by now, Dr. Ivy and I have convinced you that a rotating frame of reference
I might just pause that one for a second. I want to mention something. In grade 11, last time around, maybe not the second last time around, I should put a link for the video I'm going to refer to. But there was a video that gravity is not a real force.
So far, we've been talking about
Hang on now.
frames of reference moving at a constant.
So gravity is not a real force. And so we can actually sort of think of that now. You think about a rotating spaceship. They usually have it like a ring, and there's whatever. But basically, people could stand in this big ring if it's rotating fast enough, right? If it's rotating with a rotational velocity fast enough, then they would experience in their rotating non-inertial reference frame, they would experience a centrifugal force out. Right? In that non-inertial reference frame. Right? They'd experience that force out, and therefore they would need a normal force to balance it. Right? So in this scenario, in the non-inertial reference frame, net force is 0. right? So they have zero acceleration relative to the floor, let's say, of where they are, right? So this would feel exactly the same as standing on Earth. If this F centrifugal force is set so that it's a rotation amount equals a particular number, so if this equals Fg, what the force of gravity would be, then this would feel exactly the same as walking around on Earth. Excuse me. Right? So basically, you can see in this analysis here, this force is not real, right? That's not a real force, but yet it feels just like gravity. And so you could connect backwards and say, oh, okay, so I get it. Gravity's not a real force either. It's just a force that we're experiencing based on our surroundings, being near a mass. Okay, so in the same way, this really helps you see that gravity isn't really a real force, which is alarming to say and think about, but I'll just do a quick Google link for you here, Google search link. Not a real force is this one right here. And so if you don't recall what the details were of this video, or you haven't seen it ever, I highly recommend you watch it. Just be prepared to have your brain messed up a little bit by it. But that happens when you learn new things that are actually true and contradict what you've thought. So gravity itself is not a real force. They would actually refer to this centrifugal force as so-called artificial gravity, right? Because most humans like to think of gravity as a real force, right? So they call this one artificial gravity. But now until recently, I would have thought of this as artificial gravity and gravity on Earth as real gravity, which it is, of course, real gravity. But they're actually both artificial forces, right? They're both artificial forces. So or that makes sense to you by watching the video again, and that's supposed to say artificial. They are both artificial forces, really. But certainly this one's easy to understand that it's artificial gravity, right? Because it's gravity, an apparent gravity. It feels like gravity, but there's no mass that you're attracted to. It's just because of the rotational motion. And so that's how they make spaceships have artificial gravity. Anyway, so I should go back to, I think I might have changed my, oh no, we're good. I didn't. I was thinking I was playing from the video on my hard drive, so I thought I might have messed this up. But here we go. So question is, if these centrifugal forces are, existent in our non-inertial reference frames, why the heck don't we notice them in everyday life, right? Because we're rotating around Earth every day. You travel an incredible distance every day, all the way around the Earth as the Earth rotates with you, right? Plus the Earth is orbiting around the sun, traveling an incredible distance every year. So why don't we notice these forces? The short answer is really just because they're really small in comparison to all the other stuff we're observing. But he'll describe it.
Is not an inertial frame. Now, you've all been told that the Earth is rotating about its axis, and that also it travels in a nearly circular orbit around the sun. Why then do we find that in a frame of reference attached securely to the Earth, that the law of inertia seems to hold? Why don't we observe fictitious forces? The size of the fictitious forces which we have to introduce in a non-inertial frame depends on the acceleration of the frame. The smaller the acceleration is, the smaller the fictitious forces that we introduce.
I feel like maybe my explanation of it just being small in comparison is probably good enough. I'm not sure if there's anything more I want to show on this one, although let's see what they're showing
This
here.
pendulum is at the center.
Yeah, they're getting into pendulum and angular precession, but we don't want to talk about that yet. So that is enough of that. So in doing a very thorough job of this, I have used up a substantial portion of our time, which means but I'm only going to cover one today. So you've got a little extra time, plus you got that extra half hour of actual curriculum time and so on to look at those. All right.
Mr. Horn, I just had a question about the whole gravity not being like a real force thing.
I know. Yeah.
If it's not like a real force, then how would they think there's like exchange particles happening with that? Like back to the whole 4 fundamental forces thing?
It's a great question. I'm sure it probably plays into part of the problem, right? You probably haven't actually seen this video yet, right? Is that correct?
No.
So, use some time there. Like go and watch it. And what they talk about is they eventually talk about how if you're experiencing gravity, what's really going on is you're experiencing warpage of space-time because of the presence of mass. And they do a really good job. He does a really good job in the video of showing, the idea of a spaceship following these curved lines and how you wouldn't feel acceleration until you actually collided with a planet. And then that's when you start feeling like a gravity force, because you have to have a normal force to fight it. It's a worthwhile watch. It's pretty interesting. You might have to pause and rewind and go back 15 seconds. And, what did he just say? A bunch of times. But watch that video first, and then ask more questions. I think is probably the best thing for me to say. See if you can start to have this page feel as right as it does, it does for me anyways at this point in my journey of trying to learn all this stuff, because it's pretty complicated and weird. But gravity is, it has to do with also that if you a building and you're in free going down, how we talked about how you don't feel a gravity force, right? There's no force felt when you're plummeting to your death. You just basically that you're falling, and so your brain convinces you that you feel like you're accelerating, but in reality you don't. So we talked about that one in both grade 11 classes, but I extended last time in the last grade 11 class to this part here to really and the video starts with this analysis. And so it should be something you can follow. And then at that point, maybe you can sort of start to think about that question you asked. Maybe that is why the graviton doesn't, exist the way they're thinking it should. Because maybe they have to use the idea of space-time and warpage and so on. And maybe that's the true answer, right, for gravity itself. So it's a great question. Yeah. So
All right, I'll take a look at it after class.
Yeah, I highly recommend you do. I don't feel I can put a whole class into just watching it again, because I know half the class or a portion of the class has already seen it and so on. But yeah, it's a fairly interesting watch. So it should be something you don't feel too bad about watching on your free time or whatever. But yeah, give it a whirl and then ask again or comment on it again, at least at some point. Even if you don't have a question, be like, oh, I watched it and I kind of get it now, or I watched it and I have another question. Either way, I'd like to hear back. Good stuff. Okay, so I'll post this thing and be back at 1 o'clock.